a chance. If it's needed, we will just continue in a manner that we give enough time. And then, of course, one of the big things we would do right after we have announced and everybody's chosen teams, we will have one-on-one with me, and I will also assign a very particular TA to help you guys out, because there's a lot of resources that, I mean, thing is filled with shops. Many of you might not have used sets of tools that are literally available here, but then there are massive number of other tools we have developed. You know, we can bring lots of that into this space. And so every team will then have a very particularly assigned TA. There are certain sets of projects in which a lab member in my lab has already been working in that space. I'll rope them in. Sometimes there are other students I rope in. Sometimes there are experts from around the world. So it's a little bit about building some amount of mentor network, and we'll kind of schedule those one-on-ones right after Monday. Any other questions? I am excited to see what you guys are gonna propose, and it's a little bit of a mystery. Maybe, but if you need me before, if you want to talk to me before, just ping me. I have lots of time on Saturday, Sunday, and Discord I can do asynchronously lots of messages. So if there are teams, tag me in your team and say, this is what we're thinking about, but this is where we're stuck. There are 2 roads, fork in the road. What should we do? And I'm happy to just post a whole bunch of papers, post some thoughts. It's useful to sort of do this in an iterative way. Okay, let's do the magic show. We found it? No. No propylene glycol? Okay.
We only have polyethylene.
Polyethylene could actually also work. Yeah, do you want to just bring
In
it?
the pellet format, like where
Ooh, no, that wouldn't, yeah.
what format?
No, I think it has to be soluble in many ways. It's okay, we will test. You want to check here if there is food coloring, just briefly? Nobody has food coloring in their backpack, do they? Okay, let's come on over here. I'm going to show you guys something, you know, talking about frugal science, and Enrico and I were on a boat recently, and there was a joke, which is, you know, sometimes you can find very strange things in the middle of nowhere. So I am worried about your laptop getting shocked. So let's keep that. No, not that far. But maybe, yeah, maybe that. We're gonna use some high voltage things today. Nobody's gonna die, but this is high voltage, and we will talk about safety before I turn this on. But the purpose of this is actually, it might be fun to show you. Should we do the experiment first, or should I show you the video? No, let's do the experiment first, because you'll kind of see the, it may or may not work. You'll be like, what's going on? And then I'll actually show you kind of in its glory, what it actually looks like. What are we talking about? All we have is food coloring here, right? And something strange happens, and we noticed this almost 12 years ago in the lab, trying to do something totally different, that sometimes remarkable things are hidden in just absolutely mundane objects, like stuff that we're used to seeing. This is just a regular glass slide. And one of the interesting things about, first of all, this is a remarkable piece of frugal science technology. I'd actually forgotten to talk about this. So let's take 2 minutes to talk about a glass slide. What's so remarkable about a glass slide?
Flat.
Huh?
It's flat.
It's flat. And from a frugal point of view, this is, you know, how much does a glass slide cost? You guys, 10, yeah, between 5 to 10 cents. So this object didn't always exist, right? We had capacity to cut glass. And so what made this object exist? And I don't know if you guys have ever been to really old buildings, like one at Hopkins, the Agassiz building.
Mhm.
When you look outside the window there to the ocean, you see a really kind of a blurring type of an optical effect, like as if the world is distorted. But now when I look outside the window, it's like boom. And that's because of flatness. So you can tell the age of a building by just looking at its window. And if it had the original glass, people were making glass for centuries, right? Venetians had all kinds of glass, but nobody had a method to make a flat glass. Do you guys know how that came about? How do we make this at a billions of slides every year, perfect flatness? Anybody? Anybody in the class? Do you want to suggest? If your job was, you knew all along in the history that glass is not flat, and it was your job to invent a technology. Yes.
I think they did it more like objectives. They rub two components together and then they flatten themselves out.
Yeah. So first of all, that's a really brilliant, it's a mathematical theorem. And it also has all kinds of things in, people have asked questions about shape of a pebble. So the mathematical theorem is, if you take two flat surfaces and you put any object shape, any polygonal, doesn't matter, whatever volume of an object between, and you compress these things and then you just move, you know what shape it would form at t infinity? Yeah, it would form a sphere. So that's a mathematical theorem. You can prove it. Does it make sense why it would form a perfect sphere? Yes. Why does it form a perfect sphere? If you take two objects that don't wear, they have strength or stiffness stronger than glass, and you put two flat surfaces and then you just do that, why would it form a sphere? Yeah.
The distance wouldn't change even when it's rolling for a sphere.
Yeah. Yeah.
It's like its height, its diameter.
Yeah, that's true. Yeah. And what ends up happening is the little part that sticks out is always the one that contacts and gets sheared and grinded. So this is actually the primary way we've been able to make spheres on this planet. Perfect spheres. And actually Stanford holds the world record for the most spherest sphere in the world. And if you guys go today, at some point of time, we should show you guys too. If you go from here to the church, has nothing to do with the church, by the way. But if you go towards the church, you will walk through the material science building and the physics building. And look to your left, they have some cases. Anybody seen it? No?
Wait, outside or like?
Not in this building. Out there, you take the engineering quad, you start walking towards that way, and you pass in the first sets of buildings that are between the center quad and
Like the
engineering
palm
quad.
tree thing? Yeah.
The palm tree things on that side.
Yeah.
After this class, you should all go see it. It's the most marvelous object. It's this silver ball that's sitting there, and it has a little coat. It was designed for a gyroscope in a space satellite to measure at ultra high precision the orientation. So they needed a perfect sphere. I don't actually know if they use this mathematical theorem, but I don't know any other way to do it. It's just they grinded it at T infinity to get that, but I don't actually know how they made it. But if you read the caption, it says that this object that you are seeing, you cannot hold it, but it's in a case, is so sphere that if, you know, kind of the surface roughness of bump would be is if, you know, first of all, Earth is not a sphere at all. Earth is like a blobby thing. But if Earth was a sphere, like the errors that we're talking about would be that there is a hair lying on the surface of the Earth. If you made that sphere so large, the aberrations, so it's reaching atomic scale sphericity, which by itself is a crazy idea. So anyway, we can make, but somebody invented that. So you can make spheres. Okay, I give you that. But how do you make flat? Yes.
The lenses for the full scope.
That's correct. They are spheres, and we actually make them because of this exact same mathematical theorem. And then we do all kinds of other tricks on it, and we make aspherics, we make apertures, we change them. But the core that we start with is actually always a sphere. And this is sphere is the classic place you start with in all lenses. So when lenses form, they use the same grinding technique, but on the other side, you have another curvature. And then you start meshing it around. And some of you, if you have ever made telescope lenses or mirrors, you do very similar things and you grind for months to get a certain surface. Question, yes.
For the frugal component of this of the sphere, should you try to get it as close to a sphere as possible and then grind it and get it closer?
You can
or-
throw anything.
But
That's
for the fold scope, like what shape do you put in? You get is it
we
is it just a rough
literally
sphere?
take glass and we shatter it. And you just throw the component. It doesn't matter.
How do you make sure it's the right size?
Because there is also the
Oh, it's
load.
yep,
We're
I got that.
measuring the load and we're measuring the pressure, and you start increasing the pressure when you want. But on average, when you start, you literally take glass. It has to be the highest. You care about a refractive index. So we make zirconium lenses, for example, for a crazy application. And it's zirconium is actually tougher than diamond. All kinds of challenges then come about. But that's one way of doing it. There's actually another way of making sphere, which is what people believe Leeuwenhoek was doing, which is surface tension. You can also take glass and we can melt glass. And actually, since we're talking about glass, maybe we'll try to melt glass. Is there a Bunsen burner here? This is a lab. We will go find a Bunsen burner. Everybody has burned glass before, right? No? Okay, I'll show you guys some glass blowing tricks. This is like teach me anything. So let's blow some glass. When you take glass and you take a fiber and you heat it just the right way, it melts, it becomes a liquid. When it becomes a liquid, surface tension kicks in and boom, the sort of the minimum energy surface in 3D is actually a sphere for any given ball. And this is also, so now I'm coming close to the answer, but we haven't still answered this question. How did we invent perfectly flat glass slides? Anybody online has an answer or suggestion? Say that again. Mold and cast could be one, but then you need another flat surface. Float glass. That's why the word float glass comes from. We are literally floating glass on another medium. And in the old days, you would actually float them on mercury. Atomically flat surface. Mercury by itself, when you pour it, is atomically flat from surface tension. And then they just needed to find certain sets of things. And this is just literally water is atomically flat. And float glass, literally the word, you just needed the right density to make sure. And then literally now, if you look at the manufacturing process for this, you would see massive sheets. That's why now you can buy your windshield doesn't cost $1 billion. And it's whatever. And then once you have that, then you can also apply temperature and heat to start curving them and do all kinds of other crazy operations. But the first idea, and that happened at a very critical, perfect time. So you can actually age buildings using this trick. So if you go to Agassi, it was built. You've seen it.
I was always confused. I was like, what is happening?
Now you know.
It's like,
yeah, it's really strange.
Yeah.
And it has a really spooky, but very beautiful, because in Agassi, which is, I think, 1853 or something.
Yeah, it's old.
Yeah. And you see the ocean. And so you kind of see, am I seeing a mirage or what am I actually seeing? So
it's
anyway,
actually the basis of a false myth that like the glass is flowing, but that's
it's
not
not.
true. Yeah.
That's correct.
Yeah.
So it's very interesting that Kevin brought this up. Glass is a liquid. It's just a liquid with an incredibly high viscosity. And so glass does flow.
But not
And
at that time.
Not at that time scale. And interestingly, there's a famous problem in understanding why glass doesn't flow, because it's an amorphous collection of atoms. It should flow. People don't understand it. So there have been people who have been going out and searching for natural glass that might have formed millions and hundreds of millions of years ago. Because if we could find that, we could get the diffraction patterns and see the T0, all glass that we have, the T0 is too short. Like from T0 to now is very short. And so physicists have been searching for the oldest glass on the planet because it will actually solve what is called the glass problem. Mathematically, we don't have equations to describe properties of glass.
Wait, still unsolved?
Unsolved. Yeah, although we have like condensed matter physics and we have all kinds of scenarios, but for a given sets of atoms, you can describe properties of many metals and many crystalline structures, but glassy structures that are totally amorphous, we don't understand at what time scales they age. So if you ever find a really, really old piece of glass, it's actually incredibly valuable for science. Okay, so float glass did that. And again, a classic example of frugal science, a very clever idea, completely changed the industry. It's like, I have flat surfaces, and at the end of the day, then, you know, a lot of processing and cutting and all kinds of things happen. So that's how we got here. But we're not gonna, that was not the point. I want to do something else. Traditionally, when you get glass, it's said that it's clean, but it's not, because all kinds of things have landed on it. So now I'm going to show you something that we use to clean glass. Now this has its own, so I will hold it up here while Kevin connects that. This is sort of fun. So first of all, this object is called a corona discharge. It is off currently. I hope it works. This is just a very high voltage power supply. So I think maybe 15,000 volts or something. So I'm not going to point it at anybody, but I will let you use it if you use it safely. It's pretty simple and safe to use. And so now you can bring the camera close if you want. You can all come really close. Since I know I'm not going to get shocked, none of you will get shocked, okay? You can see there's a little wire and there is an insulator on the other side. But if I apply a very high voltage, everything breaks down. So the air, although we think is still has a breakdown voltage. Every material has a breakdown voltage. That's why thunder occurs. So what it's going to do is it's going to ionize this air. And because of those ions, we're going to see flux, which is corona, which will discharge. And so you'll see essentially thundering light bolts if we do this demo right, going on to the surface. But it has nothing to do with those thundering light. All I'm trying to do is clean glass. But it's a cool way to clean glass. And what it does, it vaporizes because of that plasma, any organics, any solvents, anything, and it re-energizes the silica bonds that are on the surface, which is the cleanest surface. And for this demo to work, I need a very, very clean surface.
And it doesn't mess up with it doesn't mess up the glass at all?
No, it's really at an atomic scale. It's stripping away everything except the glass. Yeah, so it's the surface will remain flat. So nothing happens. I come close. So look very closely now.
You turn off the lights too.
Yeah, we could turn the lights off. And
It's at the entrance.
so I'm not seeing that discharge yet because I should smell ozone. Oh, there it is.
Oh, whoa. Like the.
Do you see it? The purple glow? There. Can you guys see it? You want to bring it over here for a second? Let's bring it super close. I could also clean your laptop. Who wants to try it? Yes. All right.
It will only do that if there's things to.
No, it will continue to do that. Okay, I'm going to show you the magic trick and then everybody gets to do it. Does that sound good? Okay. What? Say that again. Nothing would happen. It's just, yeah. Because then, yeah. I mean, it's just a wire. It'll touch. Nothing. You can see the distribution of plasma, by the way, changes. So first of all, where is that color coming from? Also, where is the smell coming from? Come close here. You'll smell this beautiful, sweet. No?
Well,
I have to come very close.
maybe, a little stuff.
Oh, it actually stopped right away the moment. So I'm going to do it again. But if one of you comes close, whosoever has a good nose, who has the best nose here? All right, come on in. Okay, don't touch your nose to here. But if you're just where I am, no, you have to be a little bit closer.
Just like this.
Yeah, but not at that height. You can be at my height because gases rise.
Oh, right. Okay. You're
All right, and you're not going to trip?
No.
Okay,
I don't
you
think
watch
so.
that? All right, let's go. Let's turn the light off for a second again.
I see what you mean. Yeah.
You smell this?
Already back. Oh, wow.
Yeah, it's very clear. Come, everybody can come and smell it. Yeah,
Oh, whoa.
right?
I don't know, that's a weird, oh.
Like a sweet,
Like that smell? I don't know if I
it's
like
not
that.
about like or no like, it's just what it is. Yeah, I like all kinds of smell. You smell it? Okay,
There's
try it
like-
again,
there's
try it
like-
again,
it
it's
smells
worth it.
metallic.
Oh, yeah.
Yeah,
You
okay,
said metallic.
what is that? Anybody? It is ozone breakdown. So they're generating all kinds of free radicals and, okay, light on.
Is it
Rainstorm kind of?
It doesn't matter.
Is that it smell so much?
Those
like-
are questions you don't ask sometimes.
Is that it smell so much like rain, like when you have like the thunderstorm at all or no?
I don't know. No, I think, no, that's much more from the bacteria. Okay, so
Wait, would you?
if, oh, is there a pipette, like a little small pipetter here? Oh, it's in that side room. Because this will otherwise be too big of a droplet.
The color is,
Just food coloring.
no, the purple that was in.
It's
What-
basically ionization. So the color arises from when you ionize any gases, you generate all kinds of collisions between these very highly charged particles. He's bringing a pipette. Does anybody see a little, even the tiny pipette? Where did Kevin disappear? I know the pipetters are right there.
I don't like this.
I went to like rub a penny for a while.
Hmm.
Kind of smells like that. Licked? No.
So you can check the
Charge.
charge
Doesn't like
of it.
tingle.
Yeah, so the taste of it.
Bagels.
Wow.
We should do
That's what, you can do it.
that.
Talk about like batteries on your tongue.
All right, I think I might have unleashed some monsters here. Batteries on the tongue now. All right, so what I'm gonna do is just drop something first here. This is just food coloring, nothing interesting going on. But wait, what happens here? So you see, oh, something did interesting on it. Did contract a little bit. Well, let's just watch what happens. Watch these two carefully. You see what just happened?
Wow.
So if you all come very close, they're actually starting to talk to each other. So how does this drop know? Whoa, did you see where that, it's too much. And so if you just watch any two of them in a little bit time. Oh, let's do something fun now. Why stop at red? Now the question is, do colors know each other, right? Do they know each other? What do you guys think is gonna happen if I now swap?
They're boy, they're boy each other?
I don't know. This thing is,
Oh, this is
no, it's
paste.
a
Paste.
paste. Okay. Okay, the paste is not gonna do it. Funny, we don't have the, I'm gonna add a little more coloring just for fun. Let me see. Not the right. Move that. I'm still watching at that edge for a little bit. See if something does happen. Let's dilute it actually. Do you have some water? Yeah, just bring a tiny bit of water in the sink. So do this at home and you actually, I mean, I was just enjoying too much on the side of the plasma. You don't actually need the plasma. The first thing you notice is, yeah, actually, I'll let you guys describe what are the things that you're noticing. Let's dilute this.
Within a certain proximity to droplets.
Yeah, but it's not like they don't need contact, which is what's puzzling, that they can somehow sense each other, which was the whole point of what I want to show you guys. That within a reasonable distance of maybe even 5 to 10 millimeters, these droplets on a really clean surface have a capacity to sense each other. And now, interestingly, these ones are repelling. You notice, even when I am trying to fuse them, oh, and then this guy is starting to chase it while the other one is chasing away.
Oh, whoa.
And this is no gravity. There's no, and you see now these two are talking to each other and that's starting to, oh, there it is. That's what I wanted to show you. Do you see this? It's almost like as if these are crawling neutrophil cells. Do you see this now? It's massive real-time movement. If you want to just raise this so people can see. And now it's cornered. So it split it into two. And now it caught it. Did you see that? It fused. But the other one escaped. But now it's being tackled by the other guy here. Oh, and then suddenly this chased from the other side. Now this is trapped. And so what the hell is going on? Where could the energy from something like this come from? You can clearly see that these objects are behaving. Oh, right. These two guys have started talking now. And
Moving together.
you see that? And then there's this tiny gap between the two. It's like it's chased it away, but decided not to follow it. But the other guy is now gonna come. And then you see, first it's attracting. You see that? This red guy got attracted to the big, and then suddenly the big red guy is probably gonna chase it away. Let's see what happens. It's almost touching, but it never actually touches. So let's see. Oh, now,
Go in the corner.
do you see the chase? So the point around all of this is literally just food coloring. And now I'm going to show you guys a quick video to just tell you the, if I had an entire palette of colors, what could we actually do? So if you type ever dancing droplets, we're going to play this video and we will avoid me yapping away. So, and we'll focus on the, oh, so let's do that. Share screen. Desktop.
Yeah, let me make sure that, yeah.
Yeah, we're good. Can you guys see this? Yes? Okay, let's do full screen. And I like the music here. That's why I want to play this here, but we'll just watch it. And I won't say too much here. So all the same, that's just Sharpie lines. The beauty of science is everywhere around us. One of the things that really grabbed our attention, I wondered what was happening. It's literally as if not what I want you to see, but okay. Now that's a little oscillator. Now the gravity is pointing down. And one thread that we'll see is, oh, this is the best part. Okay, watch here. So what's happening here? So they have a sense of self. And okay, this is also what you just saw.
The physical properties of these fluids give rise.
You can see, and all this is just water and food colors. So there's nothing, there are almost, in some sense, no reaction. But now this is under the microscope. And you start to see when they chase, one of them feeds on the other in some sense. And such a simple system or a material has actually properties of what is called chemotaxis. So chemotaxis is a very complex idea in biology. You say, oh, you have to process information that's coming around from you. But a drop of water itself has a capacity to not only sense the environment, it has a molecular sensor built in, and it has an actuator, which is
exhibit this phenomenon.
Allow it to even move, because there has to be energy that has to come from somewhere, right? I mean, this is not perpetual. We've not invented perpetual motion. So after some time, it will all stop. And I'll let this play.
And that why to me is personally very exciting.
Okay, this is sort of, so a whole bunch of colors. This is a time lapse. And you see they're dancing around in many sets of ways. Kind of the point I want to make with this demo is much more about, you have an idea of a problem. You don't know the state space of physical phenomena that you could use to solve that problem. So often enough in design, the way we approach problems is we approach problems in the universe of phenomena and physical things that you know, or whatever is available on a shelf. Like, oh, this is a motor. Like I have a word for a motor, or I think what it is. While what is sometimes needed to dramatically find these alternative solutions are actually driven by also having the curiosity and the depth of knowing what is available in nature at the largest scale, and not just what has been invented, but what has never been invented. So we actually took this solution and then we applied it as a mechanism to show that you can actually build self-cleaning solar panels. We didn't invent this for self-cleaning solar panels, but once we understood the phenomena, because there's a huge problem. Currently, solar panels have very high efficiency, and then it tailors down because dust adds up on it. So a big issue on people's roofs is like, why are my panels not working? And one of the threads that we came up with is this version of using just sunlight and titanium oxides as a way to first keep these sets of surfaces and then have just rain become as active droplets, like any amount of water that's get popped on. And actually one of the last figures in that particular paper, and you know, it's sort of the connection that I'm trying to make is you have to be incredibly curious about what's happening around you to make that connection. There is no book in the world that will give you of like, oh, I need to be working on this problem, or I'm solving this puzzle. So this is the phenomena that's the best. And this is really why human creativity is important. Because at the end of the day, you need to be the one making the connection. And, you know, lots of times, unless you become a very keen observer either, and you could apply the same idea to a biological system as well. You could say, I saw this happening in a biological system, and now I have an intuition of why it occurs and when it occurs to then say, oh, I'm going to use this as a framework to solve problems. But often enough, most people do one or the other. And really fantastic problem solvers do both at the same time. And, you know, one big thing to keep in mind would be is how do you give yourself time and capacity to do both at the same time? So lots of designers are very good at identifying sets of problems and stuff, but then when it comes down to what they're actually going to implement, will be some variation of what has been done before. Many phenomenal, what are now termed as basic scientists, just have an infinite amount of information in their head, but they don't care about any sets of problems. And kind of the aspirational goal for this class and kind of the definition of a frugalist in my mind is that can live in both the worlds. And so that's what you have to aspire to do. And it's nothing like you can see this and, oh, like, I don't know anything about what's going on, but now I'm going to be curious to really go in and understand this just for the sake of understanding. It's not that at that moment, it could be 10 years pass by and then a light bulb goes in your head. It's like, oh, remember I was reading this little thing as a blurb on the side. What if I could do something with it? So it's not, we don't usually search for phenomena and things that they are useful. They exist, that's it. Our job is to just find them and explore them. And it's not, none of these things need to have their worth because you're solving a problem. But at that same time, once you know and understand them, you'll realize that your solutions will be very, they will break from what other people are doing conventionally. So there are two ways of solving big problems. One is you go to the shelf, you go to Home Depot and you find, it's called systems engineering. So lots of people will solve problems by systems engineering, and then the system gets so much more complex. You might talk about, pure water. You want to generate water from sea. How ironic that our oceans have so much water and still the world has a shortage of drinking water. I mean, just think about it. What an absurd thing to do. And frankly, if a whole bunch of people really wanted to solve that problem, you could. But then everybody's been doing the same thing over and over and over and over again. And so there's a ton of these systems that have been built, while you might say, oh, somebody who has a very deep knowledge in trying to understand really the kind of nanomaterials that can exist would come up with a very orthogonal approach to it. And so I think what I'm hoping for, and it doesn't happen in the short term, but at least a few of your solutions and ideas should really be out there and should really be connecting to what else you know in a specific field. Like you might know something about coral biology that has just been this weird fact for all this while. And then suddenly it's like, no, I want to try that to see whether something like that would play out. So as you're thinking about your projects, don't just think them in like, oh, here are all the pieces I need, and I'm going to put them all together. And so this is the best I can do. Because I am kind of forcing your hand a little bit, because you should at least be solving the problem at 100x scale and hence 100x lower cost. At least. Sometimes you even need more. And so any problem that you're starting with on Monday, we will be pushing on this idea that it really has to be mass accessible. And so the types of solutions that you're thinking about have to match that criteria. One really fun thing to do is if you go online, there's another very simple way to clean glass slide at home is you hold it not with your hand, but with a pair of tongs and burn it. So you don't need the Corona. You just burn the slide. That just burns all the organics, put it down, go to the grocery store, buy some food coloring. It's kind of ironic we don't have all the colors.
Or
No, just no on your cooking stop. Yeah. Gas. Yeah. If some of you have the gas stoves, yeah, candles don't work. Actually, candles do work a little bit. If you now go on YouTube, Dancing Droplets, there are thousands of videos of people doing this at home in their own ways. It's like this worked, this didn't work, and super cute. So candles work to a certain extent. You can also buy glass slides that are pre-cleaned too. But it's, you can see, we didn't see that here and we saw that here.
What did the initial discovery look like? Like, how did you guys?
That's it. Yeah. I mean,
Like,
we
was
were
it
doing,
accidental?
yeah, it's totally accidental. We do a lot of microfluidics, and Nate we were making sets of solutions for loading up those sets of chips. And he's like, what the hell's going on? And he pulled me in and I was like, oh, this is what we should forget about what we were doing. This is what I mean, it took us 6 years to figure that out though. So it's like from the moment seeing it 6 years later, we had everything figured out. And actually we've now written like 6 or 7 papers on this set of a system, and lots of other people got interested and other people found many other things per se. So it's a cascade. But it still takes a long time from the moment you see it to the moment you understand it. And I mean, that we know how to do that process. The problem is we don't often see it. That's kind of a, and this plasma is actually used for bonding PDMS. So that's why he was plasma treating it, because we make microfluidic chips. And so the first thing you do is you clean the glass and then you put this thing on. But because we also use food coloring for coloring our channels, it was around, and some of the PDMS had some food coloring from the past. So it's like ironic, because otherwise you wouldn't combine this object, and this object would never be in proximity other than that particular
It's
experiment.
like a Alexander Fleming moment.
That is correct. It's totally that. But again, it's the problem that everybody misses out on when they talk about these types of ideas is just the fact that, you know, are you ready to be able to observe something that is just hiding in plain sight? I think that's kind of one of the lessons I want to just make sure you all understand. Okay, so give that a try. Anybody wants to do some plasma cleaning, go for it. You will enjoy it. I'll leave this here with Kevin. You are in good hands. Please be safe. Frankly, if you did shock yourself, just like it'll tingle, but you're not gonna die.
It'll like burn you before like shocking your body.
No, it won't even do that. I've shocked myself with this thing many times. Just don't.
With this?
Yeah. Just don't do it. Yeah. It's not fun, but I am not worried, so I'm gonna let you all try it. Anybody who wants to go for it, play with it, and kind of one of the threads is when you play with it, try seeing as a function of distance, how does the spacing of the discharge changes? And then you can also think about, oh, high voltage. In my project, I could use high voltage, and then you say, oh, how do they actually make this thing? So you go down the path. If you open it, make sure you put it back together.
Yeah.
Don't open it when it's unplugged. So you can look inside that object to see what's in there. But this is the only functional one, so don't break it. And then you're bringing this back. Any questions before I disappear?
I have a question.
Questions from the conversation today, before I disappear?
Yeah, I just wanted to ask, like, it can work without even plasma, as you mentioned. So is it just like the changing the surface energy of the
Yeah, you're not changing really the surface, and you're just making it very clean. So you don't even need high or low surface energy. We're suppressing what is called contact line hysteresis. So what happens in normally without cleanliness, the surface is quite rough with all these debris, and the resistance for a drop to move is very high. By cleaning it, you've reduced that, and then you can see a phenomena that's very subtle. So nobody asked me a question of why does it work?
I think
Did I tell you already? No, I don't think it's very complex.
Is it vapor?
Actually, I'll let you think about it. Maybe this is a thing, we should leave it as a puzzle. So think about it by yourself. Why does it work? If we were all droplets, as you saw, of different colors, how are we talking to each other? They don't have telephones, they don't have cell phones. How do they even know that there is a droplet there? What is the mode of communication? And so you should sort of, I'm not going to answer it. You should think about it. Yeah, Shivam, just do a Google search on dancing droplets. Okay.
Use a Sharpie.
Yes, Sharpie is for barriers. You can write your name. It's going to follow your name. Do whatever. Sharpie is a hydrophobic barrier. It's called hydrophobic because it repels water. Let it dry first because it has its own chemicals. And then you can play games like what is the largest maze you can make that it would solve. And so every year in our intro to BioE class, we do this thing that everybody then just draws around whatever you want to draw. You can build machines. And then if you figured all of that out, then the hardest one is then can you figure out how do they know each other's color?
That one I don't.
Yeah. So how can red color know it's red and know that this is orange? And there's a little trick in that, which, anyway, I want you to think about it. Yes.
Does it just move towards it no matter what?
Is it, sorry.
And when it'll go in with itself?
Something like that is
'Cause
happening.
they
You're
both
right.
move towards it, and then once
Attraction
it
is
recognizes it then
independent
did this.
and repulsion is specific.
Hmm.
So you figured that out. Yes. And the reason they're all going down is because of gravity, because we've
So it's
tilted.
not-
That particular one is tilted.
Okay.
So we're giving it a bias to make it like a machine. And if we could have done all the dances, but with a slight bias, so then they're moving. The reason it's going that way is because there is gravity.
Hmm.
But I think you have half the answer. Yeah. Now the question is, what could we think of a mechanism that attraction is uniform and repulsion has a different term? And don't read the paper, or don't read it as yet. Then once you've kind of felt like, oh, this is hurting my brain, then go read the paper. But if you watch that video one more time, you will actually see what's going inside the droplet gives you the answers. Okay, I gotta run for a group meeting. Yeah,
Okay.
can you bring this back?
Yes, I
And
will.
if you don't feel comfortable, don't have to do this. This is just for fun.
I've
And I'll see you guys Monday.
PDMS, so
Say that again?
I've cleaned PDMS, so.
Yeah. No, you know what I'm thinking. I'm just saying, if you don't want to handle high voltage, don't handle high voltage. Yeah. And I will see you guys all on Monday. Bye, everyone.
Okay.
Can we
Okay.
just see this in the roundest object? Is that a thing? Or you have to, like,
Just go right
you
now.
go in?
You can go in. You can't hold it, but it's right there.
Yeah.
Okay.
Go straight. When you see the next set of palms, keep looking on the left. And the physics building
Yeah.
has displays, and go inside the physics building and you see many displays. And one of them has the roundest object in the world.
Yeah.
Get it?
Yeah.
Maybe meet.
Yeah, let me set it up real quick.
Okay.
Like,
Oh, okay.
What? What? I think this is
Wait,
the
we're
first
at-
one.
I have out.
You can nuke this one.
Look at that.
This is off.
Stuff right now.
And then, like,
And what is the cleaner called?
They asked the question. I'm sure.
What'd you ask?
Cleaner called the cleaner thing, that high voltage thing.
It's called a Corona generator.
You turn off the lights.
Generator. Okay, thank you.
Purple color.
See it?
You know how to touch it, just hover.
Yeah, it's like that.
Oh yeah.
Whoa.
Oh, yeah.
Yeah.
How's it feel? You feel like Tesla?
Yeah, I feel pretty powerful.
Sorcerer's Apprentice, you guys know that movie?
I think,
Do it on the water.
With Nicolas Cage?
technically it is releasing UV.
Really?
Yeah, so
Okay,
I mean it's not at a dose of like
And the deal said not to breathe it in, do it on the.
yeah, I was like I mean ozone is also like not super great for you. But I know 60 and 70-year-olds who have done this all their life, so I'm assuming the dose is not so great.
At least 6 years.
Yeah.
Wow, yeah, you can really smell it.
And it's like, wow, you can really feel the shock. Yeah, bye Debbie.
Hey, Debbie. Excellent, yeah, let's just have fun with it. Find some, do something crazy. Yeah, and also like we don't have to.
Oh, no, I'm just
Oh, okay.
watching.
Yeah, okay, and also I'll text you. Are you free all Sunday, or want to just message back and forth? We can just message back. And
You have
forth.
any electricity on?
Okay. Okay, let's do message back and forth, and then.
Yeah.
Wait,
They'll hold it only here.
Sweet. All right, you too.
Wait, I saw it like fully.
Hopefully your kid feels
touching your
better.
skin. You didn't feel that?
No, nothing. It was arcing.
It was arcing on your finger.
Wow.
Wait, what?
Yes. On
Yeah,
his
man.
finger.
Wait,
Yeah.
when? Right now?
Just now, I see it. when
Wait, which part down there?
he held it right here, and it was on his middle finger.
Like it was from here to here.
No, it was off of this.
Oh, wow.
You want to try it again?
No, do it again.
Maybe we can light something on fire with that or no? Like, what would it look if we did it with paper
I don't want to do it.
I
We'll
think
try it on this.
with the water?
It's gonna evaporate real quick.
not sure if we should try setting something on
Oh.
fire, but
Whoa, just do that.
I think that's something to do with the
it is
food.
it's drying it up.
Yeah, it's
It's
like
evaporating it probably. I think it's something to do with the.
What if
the
there
food.
was a short circuit?
You're like, dance, drop it, dance.
Whoa, oh, you're pushing it away.
I'm like pushing it, yeah. We're just bringing in food coloring. On the paper, it's probably.
I think it dissipates heat faster than
yeah.
it can accumulate.
It's so much fun.
It's ultra clean now.
Why did the paper did not burn? There's
I'm pretty sure because it dissipates heat faster than it can accumulate, so it can't reach the critical burn. Oh, I think it's
Oh.
touching.
okay.
That's so awkward. So it was fully on my skin, but it didn't do anything.
Wait, what was on your skin?
It was like I was.
Did you feel it?
arcing,
You couldn't know.
Maybe it was arcing on your hair rather than like your.
I don't know.
Yeah.
Yeah. Is it really cold now?
Oh, 11,450.
On flies.
All right, everyone. Hope you had fun. I had fun. Yeah.
Yeah, thanks, Kevin.
Thank you.
Thank you.
Bye.